Let's talk about limit and continuity in R3. Well, before we do that, let's remind ourselves of how limit and continuity works in R2. So if we have a function, we'll sketch the function. All right. X-axis, y-axis. And let's assume we have, all right, and this is x naught over here. All right, so for the limit of this function y equals f of x, for the limit to exist at x naught, limit from the left, limit as x goes to x naught of f of x, this limit is equal to, say, y naught, which is here. If and only if this limit exists, so limit exists if and only if limit from the left, right hand limit, limit from the left is equal to limit from the right, left hand limit. All right, so if we approach x naught from the left, the value we get, if we're on this path, the curve, we're going to be approaching y naught. And if we approach x naught from the right, so walking along this, we're going to also approach y naught either way. So this limit exists, even though if you remember from Calc 1 that you remember that this is not continuous at x naught. The function is not continuous at x naught, but that's not our focus now. Let's just look at limits. Now, let's try to do the same thing in something like this in R3. All right. In R3, let's sketch a function. It's actually harder, usually harder to sketch a function in R3, but I'm going to cheat a little bit. I'm going to draw the function first. Let's draw the function. And then I'm going to put my axis. Make my axis lighter in this case. This is my y-axis. This is my x-axis, I hope. And this is z-axis, all right? So let's look at the domain of the function. Let's get a subset of the domain of the function. So let's just look at this area, for instance. And then let's look at the point x naught. Oh no. Let's look at the point x naught, y naught. This point over here. Then let's try to see what the limit is or how the limit works. Okay, so assuming the value of this function, right, at x naught, y naught is z naught, and this is z naught. So if this limit exists, that means from whatever path, so if we look at the domain, or look at the subset of the domain that we're considering, and let's look at it in the xy plane. So this is y-axis and x-axis. All right, and we had I had okay, so this is our x naught, y naught, and this is the point we're considering, x naught, y naught. Okay. All right. So my point is that what I'm trying to get to is that for the limit to exist at x naught, y naught, whatever path we approach the limit from, the value has to be x naught. So if we approach this point from this path and we go up, our value has to be z naught. I have said x naught. If we're trying to approach this point from here, if we're going from there, if we come from here, if we go from there, it doesn't matter where we're approaching from, right? So if we're going along the, let's go from this point, or we want to come from here, want to go, and they don't have to be straight line, they could be like this, right? So wherever we're approaching the point x naught, y naught from, the limit has to be equal to z naught. So in other words, we can say that limit exists for limit to exist, for limit to exist, limit from every path must equal. So you might say, oh, why didn't we worry about this for R2? Because there are just two paths, from the left and from the right. That's it. Because we live on our domain is on the x-axis, but our domain here is on a plane. So we have an infinite number of paths. So the limit has to exist from all those paths. Luckily, we don't have to worry too much about these paths because there are theorems to help us compute limits in R3, theorems that we don't have to prove. But before we do that, let's give like a very loose definition of what a limit is. I say loose because I'm making it up as we go. So if the function f arbitrarily approaches L from any path in its domain, as xy approaches x naught, y naught, we say that limit as xy goes to x naught, y naught of f of xy is equal to L. All right. If the function f arbitrarily approaches L from any path in its domain as xy approaches x naught, y naught, we say that the limit of f of xy as xy goes to x naught, y naught is equal to L. All right. So what does that mean here? That means that our z naught is our L in this case. So this is our L here. All right. So if you're taking, if you are at any point here and you try to approach x naught, y naught, your value is gonna go towards L. All right. We have some theorems, some basic results. These are 3 elementary limits that are going to help us. So the first one is this. that the limit as xy goes to AB, I'm going to say AB instead of x naught, y naught, of a constant, limit of a constant is a constant, to limit as xy goes to AB of x is just a, right? And then the limit as xy goes to AB of y is equal to b. Okay, so with these three results which can be proven, then we can do a whole lot. I want to point out that this definition of limit is, like I said, it's kind of loose, but it's still complete. But there is another kind of definition that is more suitable for real analysis, not too suitable for introductory calculus. That's the epsilon delta definition. And I'm avoiding that here, but in order to prove these three elementary limits, we have to use the epsilon delta definition. But let's not worry about those. Okay, now, with these three elementary limits, we can do some examples. Let's compute these limits. Compute the following limit. Example 1. Limit as xy goes to 1, -3, or 4. The function is 4. That means our answer is just 4. Another limit. Limit as xy goes to e pi of x. Our answer is just e. And then how about this? Limit as xy goes to 1/13. The answer is just 13. All right. What do I do next? So, the laws of limits, if you remember the laws of limit from Calc 1, they apply here. Laws of limits. All right. Okay, so let's assume that the limit as xy goes to, let's do AB of f of xy, assuming this limit is equal to L, and that the limit as xy goes to AB, that's the limit of g of xy as xy goes to AB, is equal to m. Then we can do a bunch of things with this. If we know this limit, then the limit of f of xy plus g of xy as, I'm gonna skip this x. Well, I'm so lazy about writing. Xy goes to AB is equal to L plus m. So if it's xy, f of xy minus g of xy, then it's just going to be L minus m, and so forth. Okay. So likewise, the limit of maybe a constant c times f of xy is just going to be c times L. And then the limit of f of xy times g of xy is just going to be Lm. Then we can talk about limit of f of xy divided by g of xy. And all these limits is the limit as xy goes to AB, xy goes to AB, xy goes to AB. All right, so this is just L over M, but then we have to make sure that M is not equal to 0. How about the limit as xy goes to ab of f of xy to the power of some p, where p is a real number. This is just L to the power of p. Now, all right. With this, we can write a theorem that is going to help us. We can use, each of this is actually a theorem. But what this theorem is going to, what this result is going to boil down to is that for polynomials and rational functions, for polynomials and rational functions, simple substitution works for a and b, for ab in the domain of the function. All right, with that, we're very equipped to solve some limit problems. So let's do more examples. Example 1. Let's look at the limit as xy goes to 2(8) of 5x squared y plus square root of xy. Okay, so we're just going to substitute, right? 5 times 2 squared times 8. This is very easy, right? Square root of 2 times 8. So we get, when I did this, I got 164. I would like you to check my answer. Now, how about this? Limit as xy goes to 0, 0, 3x squared over y squared. So let's try to substitute. Limit as xy. How about, let me do 0. No, let's change it. Let's change this to 2, 2, 1. So this will just be 3 times 2 squared over 1 squared. So this is just 12. All right. Now let's try another one. The same problem, but something else. Let's do 0, 0 of 3x squared over y squared. Okay. So this is just going to be 0 over 0. So this is undefined. So limit does not exist. We can't do much. But there are problems where the limit doesn't exist, or it looks like the limit doesn't exist, but you can actually do more to get the limit. So let's look at 4, 4. Limit as xy goes to 4, 4 of x squared minus y squared over x minus y. So if you plug in 4 and 4, you end up with 0 over 0. But we can do more. We can do limit as xy goes to 4, 4. That's 4, 4, not 4y. And then you can do factor by completing the square. X plus y, x minus y over x minus y. And these happily cancel, and you plug in 4 and 4 for x and y, you get 8. All right, let's try another one. How about limit as xy goes to 4, 1 of xy minus 4y squared all over square root of x minus 2 square root of y. Again, if you plug 4 and 1, you will end up with 0 over 0. So let's see what we can do. We can do factorization. If you factor out a y at the top, you'll be left with x minus 4y. Interesting. But then we still have root x minus 2 root y. Now let's multiply by the conjugate. If we multiply by the conjugate of root x minus root 2 root y, says root x plus 2 root y, all over root x plus 2 root y. What do we end up with? We end up with square root of y, x minus 4y, times root x plus 2 root y, all over the bottom is just going to be root x squared, which is just x, minus 2 root y squared, which is just 4y. All right? So it's just root x squared, which is x, minus 2 root y squared, which is 4y. So things are going to cancel out, and we're left with y times root x plus 2 root y. So what is y? Y is 1 times root x root 4 plus 2 root y. So this is, let's see, 2 plus 2, which is 4. Okay. Now, let's do some proofs. Let's prove that the limit as xy goes to 0, 0 of x plus 3y over x minus 3y does not exist. This limit does not exist. Well, you could say, hey, can't we do more, like multiply by the conjugate? We actually cannot. Try it. Try multiplying by the conjugate. Try a few things. It won't happen. So, it doesn't exist. But we need to be able to show that it doesn't exist. Remember, if the limit exists, then on the xy plane, if we approach the point 0, 0 from any point, the limit should be the same. So to show that the limit doesn't exist, all we have to do is to find two paths that don't give us the same limit. All right? And there is a way of doing that. There are methodical ways of doing that. One way is to choose a family of paths and then realize that, oh, if you take one member of the family, you get one limit. If you try another member, you get another limit. And for this limit, this problem, I'm going to choose the paths y equals mx. So y equals mx look like this. Lines like this line, right? Or some other line. They're just infinitely many lines, but they're just lines that look like that. Lines that look like this. Lines that look like this. And so forth. So we're approaching the origin. We're approaching 0, 0. Okay? So these lines are y equals mx. Let y be equal to mx. What do? I go to my problem and I rewrite everything in terms of mx, m and x. So if I say limit, we're looking for the limit as xy goes to 0, 0 of x plus 3y over x minus 3y. This now becomes limit as xy goes to 0, 0 of x plus 3mx, because y is mx, over x minus 3mx. Okay, but we can do some magic here. So this will be limit. Everything is in terms of x now. So this will just be limit as x goes to 0 of factor out an x over 1 plus 3m over x 1 minus 3m. So you can cancel out this. And then as x goes to 0, as the limit goes to 0, your answer is just 1 plus 3m, 1 minus 3m. So your answer depends on m. Interesting. So we can say if m is equal to 1, for instance, then the limit is equal to, plug in 1 at the top, you get 4. Plug in 1 at the bottom, you get negative 2, which is just negative 2. However, if m is equal to 2, the limit is different. The limit is equal to 1 plus 6, which will give you 7, right? And then 1 minus 6, which is give you negative 5, I think, which is not equal to 2. This is so not equal to 2. So something ain't right. This is not equal to 2. All right? So what have we shown? We've shown that if we approach 0, 0 along this line, our limit is 2. But if we go along the green line, our limit is negative 7 over 5. But limit has to be the same thing from every path. So that goes your proof. Since the two limits are not equal, since limit along two paths are not equal, we can conclude that limit does not exist. I'm going to stop here with my really truncated grammar. All right, I'll see you in class, or I will see you in the next video if you're not taking the class.